Okay, welcome back. So in the previous problem, we found the arc length of a length of a line segment, which again we could have just done with the distance formula. Here, there's one other thing we know how to measure the arc length of without having to use calculus, and that is the arc length of a circle, right? So here our problem is we have a circle of radius 1. We want to find the length of the arc subtended by an angle of pi over 2. Uh, and we're going to do it first with the arc length of a circle. So from trigonometry, you might recall, or maybe you don't recall, but I'm going to help you recall it, that if we have a circle, and our circle happens to have a radius of r, and we have an angle, a central angle of theta, then the arc length of that angle, we say that angle, arc length, that angle subtends the arc. It's the two ends of the arc, right? Then recall that if theta is in radians, then the arc length is just the radius times the radian measure of the angle. S equals r theta. So if our central angle is pi over 2, in other words, draw my circle back in here, and I have my pi over 2 angle. We'll do it in the standard way for pi over 2, which would just be this angle right here, 90-degree angle. Then the unit circle as a radius 1, that's the circle we're dealing with here. And so the angle is pi over 2. So by our arc length formula, S is equal to pi over 2 times 1. And so we know that that length is pi over 2. Okay, so that is if we do it using the arc length. We get an answer of pi over 2. Now we're going to do it using the arc length formula. And we're going to see that we also get pi over 2, but it's going to be a whole lot harder. But I just want to use this again as another example to verify that this arc length that we're doing is actually working. The arc length formula here is actually working. So for arc length, we need to translate this circle of radius 1 into an actual equation. So let me draw in my x and y axes here. And so let me draw in a circle of radius 1. We're going to move him over here. And there it is. So basically, we're looking at the arc length here, right here, just our pi over 2 angle. That's going to be running from the x point here at 0, 1, to the x point here at 1, 0. So what we need is we need to be able to talk about the derivative of this curve. Now, we don't have to do the whole circle. Just need the circle that contains the part of the arc that we're worried about, which in this case is this piece right here in the first quadrant. So the equation of the unit circle, remember, is x squared plus y squared equals 1. And then we can solve for y. And normally, of course, we'd have plus or minus, but since this is in the top half of the circle, we can just get by with the top half of the circle. Y equals the square root of 1 minus x squared. Okay, so that's going to be our function there that we're going to have to do the arc length of. Of course, to do that, we need to talk about its derivative because that's what arc length calls for. So I'm going to rewrite that as 1 minus x squared to the 1/2 power. And now we're going to do our derivative using the chain rule. Except I'm going to, this time and probably from here on out, use the chain rule in a very abbreviated manner. So you can again go back to the longer process that I showed you when we were reviewing. If you're more comfortable with that process, go back up here, right where we're writing it out with our U and F, right, and doing it in steps. You can certainly, continue with that same process, but here I'm going to use an abbreviated approach, and many of you are probably already doing it this way anyway, saving a bit of writing. So by the chain rule, I do the derivative of the outside function. That's the stuff to the 1/2. That would be 1/2 times that stuff. Now to the minus 1/2 by the power rule, and then times the derivative of the inside part, negative 2x. So that gets me down to my y prime. When I simplify, the 2's cancel out. I get negative x on top. And then that stuff is to the minus 1/2. So that's going to come to the bottom and become positive 1/2, or square root of 1 minus x squared. So there's my y prime function. There's my y prime function. Okay? And so now we're ready to do arc length. Arc length is going to be the integral between your x values, 0 and 1 in this case. 0 and 1. So integral 0 to 1 of the square root of 1 plus y prime squared. So 1 plus negative x over square root of 1 minus x squared, all of that squared, dx. Okay. And then we just start to simplify that result and see what we can do with it. Okay, so integral from 0 to 1 of the square root of 1 plus x squared over 1 minus x squared dx. And so to simplify further, I'm going to need to get a common denominator for the two things inside the square root. So continuing on, integral 0 to 1. When I get a common denominator, that is just going to be the 1 minus x squared. And so, of course, for 1, I'd have to multiply the top by 1 minus x squared. That would make its numerator be 1 minus x squared. And then that's plus the other x squared. And this is dx. So the x squareds go out. The x squareds go out. And I just have square root of 1 over 1 minus x squared. So I can rewrite this now. Square root of 1 is 1 over the square root of 1 minus x squared dx. And now we come to the question like, well, now what? Right, now what? Well, you see there's a problem here, right? My basic substitution, u equals 1 minus x squared, is going to call for a minus 2x to go with my dx. And where in the world is my minus 2x at? Right, there's my dx, but I don't have a minus 2x. I don't have an x at all. Right, so this is one of those integrals, going back to Goldilocks and the three integrals, this is the mama bear integral. Right, there's not enough there. Right, her porridge was too cold. It didn't have enough heat. Right, it was deficient. We don't have enough to carry the substitution through. Well, eventually we're going to have an answer to this thing, which is going to come up into chapter 8. That's a little that's a little disheartening. Right. So what do we do now? Do we just stop this problem? Why'd you give me a problem that just stops and now I can't do it? Well, we can do it. We just have to recognize a fact. And that is that 1 over the square root of 1 minus x squared is something we have seen before. Something we have seen before. In fact, we saw it on our very first day when we looked at derivatives of inverse trig functions. And we found that the derivative of the arcsine function is 1 over the square root of 1 minus x squared. And so here we have to recognize it. Later on, there'll be a method and approach we can use to work it out, even if we didn't realize it was. But for now, we have to realize that thing is the derivative of the arcsine. So therefore, the integral of that is going to be the arcsine plus a constant. Since we're doing definite integrals, we won't be worrying about the plus a constant part. So going back to our problem now, based on that new observation, and by the way, this chapter 8 is going to be looking at one of the things we're going to be looking at is called trig substitutions. That's what we're going to eventually see to do this problem. But for now, we recognize that as the derivative of the arcsine function. So the integral will be arcsine x, and then evaluating it between the two endpoints 0 and 1. So we get arcsine of 1 minus arcsine of 0. Remember, these are in radians because anything with calculus and trig functions, we're talking about radians. So arcsine of 1 is asking what angle in the first or fourth quadrants between negative pi over 2 and pi over 2 gives me a sine of 1. And we say, well, we know that is pi over 2. And then what angle gives me a sine of 0? Right? What angle gives me a sine of 0? And we say to ourselves, well, that would be 0. Arcsine of 0 is 0. Pi over 2 minus 0 finally is pi over 2, which does agree with our original way of doing the problem. Much, much easier with simple circular arc length. Okay, but I did these first two examples to show you that our arc length does give us answers that line up with other things. Now we're going to be turning it over to working out equations where functions where we can't really compute the arc length with one of these other methods. Okay.